All right. Well, welcome to the February 2018 Lancaster AI meetup. My name is Rich Everts, and I'm excited to have everybody out today. We actually got a couple of great talks today. So we're going to do an intro to computer vision and CNNs, convolutional neural networks. And we're also going to do an introduction to GANs, which are generative adversarial networks, which are kind of like a cutting edge content creation. You'll hear a lot about them, and they're getting a lot of positive and negative press, so it's going to be great to just dig into those a little bit as well. So my name is Richard Everts. I'm helping to organize this, and I'm the co-founder of Suji, which is a home AI for disabilities like Alzheimer's and autism, and we're based out of here in Lancaster. And computer vision is something I've studied for a long time, and definitely looking forward to digging into it with you here. There are some refreshments at the back table. Feel free to help yourself. And it's 6:30, so let's get on in here. So what we're going to need to do is, when we're talking about computer vision, we're going to need to take a look at a couple of things. If you want to understand how it works for computers, we first got to understand how light works, and then we're going to look about how humans work with light, and then we're going to transfer that into how computers work with it. So how does light work? Well, this is a pretty straightforward thing. You guys might remember this from a basics physics class a number of years ago. The light is two things. It's usually a particle or a wave, and you can do a lot of experiments on it to make it appear as two different things. So what we're concerned with is here, if you'll see up top, you see the wave. As a wave, you have the left-hand side here, you have a high amplitude wavelength, which means that high frequency. So the little sine curve is really compact together, really squished together, which means there's a lot more energy in it, right? So that's a short wavelength with a lot of high energy in it. And then if you go along this little wavelength chart here, you end up at the end, by the time you get to broadcast band and radio, you have really long frequencies like radio, and that's how it's able to travel around the Earth very easily. But it doesn't have as much energy in it. Now what we're concerned about is this little spectrum right here, which is a spectrum of visible light. And it's tough to see. I'm not sure what's going on with the projector, but this is actually supposed to be bright red. It is on my screen here, so just imagine that this is bright red, okay? So it goes from blue to red. And visible light, the blue spectrum is about 400 nanometers, the distance between the tip of one to the tip of the next, okay, in terms of the wave. 400 nanometers with about 3.1 electron volt. That's the actual energy that's in here. And as it moves forward through this spectrum, by the time you get to the red spectrum, it's about 700 nanometers, which is almost twice as long, and it has about almost half the energy at 1.6 electron volts. So that is how light works as a wave. Now, the interesting thing here is we also need to look about how light travels and how it bends, because this is important to computer vision. So, as you can see here on the left-hand side, this right here, imagine this being just a wave of consistent light. It never is this perfect, but it works out well here. And one of the things you have to understand is that this is a convex lens, okay? Which means that it is shallow on the ends and it's thicker in the middle. Your eyeball is a convex lens, okay? The front of a camera is a convex lens. Now, why are these important? Well, because light travels slower through a medium like glass versus through the air. So it travels quickly through the air. So what ends up happening is that at the top here, it travels the fastest. It's not slowed down until the very end, and then just slow down just a little bit because it hits the glass just a little bit, and then it gets bent. And that's what this convex lens does, is that it allows these, which have to travel a further distance, to travel faster, like a little runner going around a track. If you ever we just watched the Olympics. So it gets refracted and bent to this one little point here where it combines, called a focal point. And that's how a convex lens takes light and focuses it on one point. And the focal length, you might, if anybody here is into photography, is the distance between the middle of this lens and the focal point. So a focal length of 35 millimeters, well, that's what it is. It's the difference between this center of this point and your focal point. Okay? So let's take a look at how do humans handle light. I know this is kind of, I didn't come out for AI. How am I looking at biology? But it actually plays a huge part in how we understand computer vision. So how do humans handle light? Well, at the front of your eye, which is up here, you have your cornea, right? And then you have your pupil, which is, the pupil is the little black thing in the middle, right? And then you have the little color around your eye, right? Well, that little color stuff around your eye is actually, its only purpose is to open and close your pupil, right? So it controls how open or closed it is. Now, that is the same as what we call an aperture. So how much light do you let into an eye? The more your pupil is open, the more light that comes in. That's why at dark, when it's dark out, your pupils get really big. Or when your body perceives dark, your pupils get really big because they feel like they need to let in more light. Okay? So that light comes in here, it hits this lens right here. And so it's a convex lens, so it hits a focal point. And that's pushed into the back of your eye here. And the back of the eye, called the retina, okay, has all this fancy stuff going on. And I'm going to explain what it is because we're going to get into some nitty-gritty details about how it works in a computer. So it's important to know that the light comes in here, it's controlled by the pupil, how much light comes through, and sent back to the retina. Okay. So I know you can't see some of this just because the projector's not sharp enough, I don't think. But this is, how do humans transduce light? Transduction. Transduction is the conversion of energy from one form to another. Okay? So we have to take light, which is an electromagnetic element, or substance, I should say, and we have to convert it to an electrochemical substance. Okay? So we have to make this conversion. So how does that happen? How does that transduction happen? So what ends up happening is light passes through here, hits this, and it comes into these rods and cones in the back. Rods and cones are, the cones, which do color vision, are usually 3 different colors. You have red, green, and blue, and you have twice as many cones that are green than all the others. So it's actually a 50% distribution of green, 25 red, and 25 blue. And then you have your rods, which are monochromatic vision. Now there's 120 million of those, and those handle a lot of motion. Okay? So cones and rods handle this information. Now, how does it actually transduce this stuff? Okay. So this is nitty-gritty, but it's important because we're going to take a look at how a machine does this too. So in the back here, you have these rods. We're going to use the rods as an example. And you can't really see it here. It's tough to see the focus, but there's these little slices at the end, and they're like little discs that are layered on top of one another. Okay? And inside these discs is this substance called rhodospin. Now, rhodospin is a protein that's in there, and inside rhodospin is a molecule called retinol. Okay? And it's tough to see here, but you can see it. It's kind of like a helix that's kind of curved down. Okay? And when light comes through, a photon comes through and hits this retinol, it ends up changing the form of that molecule. Okay? It changes the form because the energy gets distributed in the molecule and it changes the form. So as the energy transfer happens, the form of the helix changes. Normally it's down here and then it straightens out. And when that happens, it starts this transductive cascade. It's a phototransductive cascade, I think is the official biological term. But it sets into wheel a sequence of actions. So by changing its form, it drops this other protein called transducin, funnily named, and it's like a drop ship, and it starts this process, and it hits these proteins. What ends up happening is that it stops the rod or the cone from firing. It actually clogs the pipes, which is kind of odd. You would think that when it was excited, like we talked about last time with the neural network and it fired, that would tell you that something's going on. But it's actually when it stops, the body reacts to it. And one of the things that you have to remember is when you're looking at light and when you're looking at color, what you're actually looking at, like this table here, is brown. Okay? But really what it is that the table reflects every or it absorbs every single light spectrum color except brown, because brown is what's actually reflecting back into your eyes, right? And so you're actually not seeing something that's brown, you're seeing something that is not brown in terms of its qualia. I know it's kind of a little conundrum there, but that's kind of how your eyes work here as well. Okay? So they respond to this, and then these bipolar cells and the ganglion cells send that information back. So that's the transduction, yes?
So when it turns off,
yep.
Do you see all the other colors except for that color, or do you see that color? That's, you know what I'm saying? Like whichever color is associated with those discs.
Yeah, whatever color is associated, that's what fires back into the optic nerve and gets sent back.
When it shuts off?
When it shuts off, yes.
Interesting.
Yep, they're by default on. So what ends up happening is that your eyes, and most people know this, that they kind of cross over in your brain and get sent back here, and you have through the optic nerve and the optic chiasma, and then you have this lateral geniculate nucleus, this LGN. Now, the interesting thing here is that the control apparatus for your eye, okay, so the pupil dilation, what we call saccades. If you're not familiar with saccade, it's that most people think that their eyes kind of move about a little bit, but what it's actually happening is your eyes are constantly scanning. You see about 2% of a visual field, and your eyes are constantly scanning across, down, all the time. It's that micro motion which creates vision for you. And so then it gets into this LGN, which starts extracting this stream of information, like contrast, color, motion. And by the time you get back to the primary visual cortex, you're dealing with things like depth, reassembly, and basic interpretation. Now, I know this seems like it's boring in some ways, nitty-gritty, but here's where you're going to start seeing some duplicative effects. So when you get back to the visual cortex, which is in the back of your brain, right here in the brainstem, okay, above the brainstem, right here in the back of the head, it's tough to see, but you have like different areas, V1, V2, and they're separated by colors. So what happens? So this signal has gotten sent from your eye all the way to the back of your neck. Well, in V1, which is like the center, there's these neurons, and these are lists of action potential firings. So it responds to certain things. So if it sees let's say a couple of rods, like 3 of them in the back of your eye that are in a row, like 1, 2, 3, and it's in this shape in the back of in the retina that got sent back, it fires this much. If it's in this position, it fires that much. It's almost like it's doing edge detection. Almost. It responds. This one neuron responds to this configuration of an edge detection. That's what happens in V1. Very basic. The most simple setup that you can have is right there. Now, it gets passed up to V2. Now, these are also single neurons. And by V2, you start to get X patterns. You start to get semicircles, triangles. You're starting to get patterns, more complex patterns when you get up to V2. One neuron. By the time you get up to here, which is IT, which is a much higher level in the visual cortex, these are hands. And here you have a full hand, and you see it firing. It's one neuron responding to this. And then this is a hand-drawn hands until you get to like a really small mitten that barely looks like a hand. That's a measure of the neuron firing. And you can see it. It's actually responding to hands. And so what's happening is that you are responding to edges, patterns, and then you're actually recognizing it at the object level as it gets passed up the visual cortex. Okay, enough biology. So how do computers do it? How do computers do it for computer vision? Well, this is what we have for a DSLR camera. So a DSLR camera has a bunch of lenses in it. Now, it doesn't have just one convex lens in it. A lot of these cameras have a bunch of different lenses in it to move light in specific ways. But we're just going to pretend like it's one convex just for the sake of this example. And then what ends up happening is that light gets transferred back here. Now, if you're looking through a DSLR lens, you look through the viewfinder, you see the image, right? You remember seeing the image. So what's happening is there's a mirror in here that is taking the image from the lens, shooting it up here, bouncing around. That's what you're looking through your viewpiece. Now, when you click the button, the image in your viewfinder disappears usually if you're using like a 5D Mark II or some other kind of professional DSLR camera. Even your phone will generally freeze for like a microsecond, And what's happening is that the mirror that's in here is coming up to allow the light to come through here. and you have this thing called a shutter and a sensor. The shutter, if you ever heard of shutter speed determines how much light you let through. A very fast shutter speed, which is like 1/4 or whatever, 1/16, is it goes down and up really quick. So only a little bit of light photons are allowed through. But if you let it expose for a long time, you go that snapping that you hear if you're using a big DSLR camera. That's the process of the mirror coming up and the shutter coming up and hitting the sensor. So that's a little bit about how it actually gathers light. It lets it come through here. Again, the focal point is back, it changes the focal point to right on the sensor. Now here's interesting. Okay, so just like the eyes transduce light. They take light. Here we have to figure out how to take electromagnetic signal and turn it into a digital signal. How do we do that? How does computers do that? Well, I'm going to use a CMOS, which is generally what you find in most consumer-grade cameras today. You could do CCD, I believe, which is used in a lot of satellites, and when you need some specific high-quality cameras, they still use them, but CMOS is generally what you're going to run into. So this is what that sensor looks like. It has these little bubbles on it, and it's tough to see, but these gray ones are actually red. Okay? So you have red, green, and blue. Just like your eyes, greens, 50% of this layer is green, 25% red, and 25% blue. So you have these little bubbles over there. And what these bubbles do is they only allow light of that spectrum to enter this little bucket, which is underneath all of them. That's the only light that they allow into there. So a blue one will only allow blue photons at that wavelength to enter this bucket. And then you have this silicon substrate, and essentially what happens is when it goes in there, the electron energy gets separated, and this bucket collects the electrons, and it knows what approximate voltage is based on the color, right? So it basically collects these in here. Is what's happening, and it's collecting them. So the shutter lets light in, light gets distributed across this. This is called a Bayer pattern, named after a guy from Kodak, of course, and it collects in a bucket. And what's going to happen is that after a specific set of time, it's going to stop, calculate, and all these electrons that are in here, that energy gets changed to a voltage, which then, of course, can be changed to a 1 or a 0. Okay? This is actually a pretty neat little process of the silicon substrates. So, okay, so let's keep taking a look at processing the light into the data. So here's the light, here's the sensor, right? And it gets transferred. Now you have these buckets, red, green, and blue. And what we're going to do is to get from the raw voltages to something that we can really use, a JPEG RAW format, okay, which is often what you'll get in your DSLR cameras. You can get this RAW format, which is huge. It's absolutely enormous. But it has the most color accuracy that you can possibly get. So to get from here to here is a process called demosaicing. Now there's a reason I'm showing that to you, because this is going to come up later. So what happens is there's usually a 2x2 or a 3x3 matrix, right? That, and there's a lot of heavy math in here. And they look at these voltages and say, well, based upon this thing with this amount of voltage, the color at this point should be a red, green, blue. If you ever used Photoshop, you know, RGB. That's how you can denote all the colors. And it calculates what this one piece should be. And then it goes straight across that entire sensor, one by one. So it goes here, and notice how it changes. It goes across here, and it figures out this one. Now, you might be asking, well, how does it figure out the edge ones? Well, it creates this thing, these zeros on the outside, which we call padding, and it figures that out into the calculations, and that's how you get your edge values of your JPEG RAWs. And now, you have images that you can work with, okay? So, processing features. Well, remember how the brain took a look at those little edges and then started building up representations? That's what convolutional neural nets are doing. So let's take a look here, real quick, at an image kernel. This is a great website here. Oop. Okay. So what you have here, notice this right here is your 3 by 3 matrix that we talked about before. It seems that computers really like these matrices. So what it does is loads up an image, and let's say we wanted to do an outline. Notice how the image changes, and this is an outline of this image. It's really tough to tell since this is probably like a 20 by 20 image or something really small that they blew up. That's why it's pixelated. So what ends up happening is that in order to get an outline, you have a matrix which is designed to be dragged across an image. So it'll basically take that -1, -1, -1, -1, -1, 8, -1, and then the bottom negative ones, and place it over these guys here, and it'll do a quick multiplication. So if 255, right, because white is 255, there's 256 values, white is 255 times -1, and then there's, you know, it looks like they're almost all white. So you take all those times -1 or whatever is in the array and add them together. You get a total of 3. So what color is 3? It's tough to see here, but right here is 3. Okay? 3, if 0 is pure black, 3 is like really, really dark gray. Okay? And that's how it goes through it. This is an outline matrix that it drags across there. Okay? That's how convolutional nets are able to build images. So this is what we call a feature map, an outline feature map of this one. Okay? And you can do that for all kinds of things. So if you're coming down here, you know, that's the outline of that image. You can look at a blur. You know, what does a blur look like? Well, that's the blur matrix, and it gets drug across the image. That's what a convolution is. Okay? So let's go back here real quick, and let's keep going here. So to give you an example, this is how features are built. So if you take an image and you go through these layer 1, which is like your things like your outlines and your edges and everything like that, you have very simple stuff in layer 1. And then you basically do the same thing to all those images, and you start to come up with patterns, small patterns that you can start seeing form in here, semicircles and circles and corners of things. And then as you go up through here, by layer 3, you're starting to get pictures of people in there, and like semi-faces. And, you know, up in there on the upper left-hand corner, you start to see patterns that match this stuff here. So they start to arrive. And then by the time you get to 4 and 5, you end up seeing, I know it's tough to see because of the color here, but you're starting to see full faces and dogs and animals and everything like that in the actual features. Just like the human brain, we're building that up over time. Yeah?
The colored part that looks like real images, is that just real
Yep.
examples?
Yep. So these are the examples of where these features were drawn from.
Cool.
Yep. Okay, so let's go ahead and dig into the code a little bit here. All righty. So how are we doing on time? Good. Okay. So I'm using Jupyter Notebook here, and we're logged into Paperspace because I don't have a GPU on this thing, so we're going to be using Paperspace. And this is image classification with convolutional neural networks. This is pulled from the FastAI course. I've used it there and just kind of modified it a little bit for what we're doing here. I do highly recommend the FastAI course if you're interested in AI. It's free. It's run out of San Fran, and these guys are amazing, like really cutting edge stuff. And I can't believe they're giving it away for free. So definitely check it out. There's no timetables or anything. I would definitely use it. Here we're going to be using PyTorch. You might have heard of TensorFlow because Google is really good at marketing. So they really put TensorFlow out, and a lot of people are using TensorFlow. But PyTorch is being used by a lot of people as well doing research. So it's a great platform and framework to be able to use. So what we're going to do here is we're going to do a classification of Jack Skellington versus Santa Claus. Anybody here ever watch Nightmare Before Christmas? Okay, so everybody got confused about that, all these people, but we're not going to be confused here, I don't think. So let's go ahead and take a look here. So if you're not familiar with Jupyter Notebook, it allows you to put code in here, and we just kind of process it as we go through. So I'm just going to explain what's happening here. These are just some things for Jupyter Notebook, so I'm not even going to bother here. And we're going to import our libraries. FastAI has some stuff built on top of PyTorch, which enables it to do some neat things. So I'm going to load my data here. In a convolutional neural net, we load our data. It's under Santa Jack. All right, and CUDA is available, which is good, and this CD, there we go. Okay, so let's take a look at our directory here real quick, and we can see that we have a validation, we have our training, and we have our test set.
Oh, the red came back.
Uh-oh, what was that? Hold on.
Aha.
Ah, look at that. Loose cable. That, you know, it's like that always reset your computer thing. All right. Well, this will help. So let's take a look. We're going to take a look quick at our data set. That's almost the first thing you always do is you just take a look at your data set, get an idea of what you have here. So let's take a look at some, we're going to pull off 5 random images. Python here, that's just saying from the beginning of the array to 5. And we're going to take a look here and let's actually read that in. Okay, so this is our picture. That's a picture of Jack Skellington right there. Okay, great. So that looks good so far. What's the shape of our image? So it looks like we're at 720 by 1280, and there's 3 layers. Remember that RGB? Well, that's what that 3 is. And then 720 by 1280 is the resolution, the size of the image. So if you actually look at the array here, you get a bunch of 255s. Okay, there's a lot of dots in there, which you're not going to see. But really what that means is that there's a lot of white in that image. And looking at that image, that's what we would expect. We would expect a lot of white in there. So this is going to be, we're going to use a pre-trained model using a ResNet 34 architecture. And the interesting thing is that back in 2013, accuracy of above 80% was considered state of the art. State of the art to get that. So we're going to do it here in 3 lines of code, really, 4 lines of code, and it's going to happen in about 20 seconds. Okay? So what we're going to do is we pick our architecture, we load our data into a data object, and then we create what we call a learn object here. We're using a pre-trained model, and then we're just going to fit the model to the data using a learning rate of 0.01 over 5 epochs. Okay?
How big is the data set?
So we're using a form of ImageNet for the features, but for the actual data set, less than 100 images per. So we're,
Bosses and jacks.
yep, of Santas and Jacks. So it's a really small data set. So hopefully because I'm using a GPU, at Paperspace, it'll go fairly quickly. There you go. So as you can see on epoch 0, I had 69% accuracy. And by the time I hit the second epoch, I already had 97% accuracy on there, which is pretty good. Pretty good. Remember, state of the art was 80% in 2013. So let's look at this a little bit. Let's see here. I'm just going to cycle through these because they're not that interesting. These are just some random functions we're going to have so that we can plot and look at things. So let's look at the things that we correctly classified here. All right, let's load these up. There we go. So these are things, and this will tell you the accuracy of them. So we got this guy, 99%, that was Santa Claus. And this is, you know, that's our guy. It goes from 0 or 1 was the classification, so it helped there. And let's look at incorrectly classified. I think we didn't have any, so that's going to come out as 0. So these are ones that we were most sure were Jack Skellington. Okay, so obviously these, there's really no arguing that these are Jack Skellington. Now the reason I'm showing this is because we're going to take a look at the most correct Santa and then the most incorrect, or the ones that it was having the most challenging with. So those are the ones that look most like Santa and it pulled out the features of a Santa Claus. This is showing you the importance of a data set. Now, that one was the one that got wrong and it thought, maybe that's Jack Skellington there. But let's look at our most uncertain predictions. These are the ones that was most uncertain about. Honestly, I don't understand that one. But it's funny is because you got to remember that when you're doing computer vision, it's looking at pixels. It's not understanding what's going on. They've done famous studies where they've changed a couple of pixels in an image and completely screwed up the model. And so it could look at a person, and you underneath of it on one of the layers, you put a small couple pixel changes, and the computer thinks it's an ostrich. Okay? It doesn't really understand the image. That's why you need a ton and a ton of data in a deep learning network to kind of overcome a lot of these issues. And so it worked okay here because Jack Skellington and Santa are very different things. But that's not always the case. And the subtleties are sometimes very challenging. So I'm not going to go into this a little bit too much, but there are things to help you choose learning rates now. I'm going to show you what I mean by this. Okay, that's data augmentation. We need more data. Okay. So generally what's happening is, and Wes talked about this last meetup, you have this gradient descent. So basically you have this mesh. And the way Wes was talking about it last time was, a blind hiker, closing their eyes and feeling the ground around them and saying, this is going down this way, so I'm going to step this one small piece, right? And so the learning rate is how big of a step you're taking, okay? That's what it is. So if it's 0.000001, you're taking a really small step. But if it's only 0.1, then you're taking a big step, right, in that direction. And so that's what this mesh represents, okay? And so what they're actually able to do now, specifically in PyTorch and FastAI, is they are able to adjust the learning rates as they go through. And so that way, at different sections, you can say, okay, so I feel this, this is a steep step. Maybe I want to take this one a little bit further. Or this one, I might not want to go that far. And it'll allow you to traverse the different measures until you get into a bottom point, which is your goal, is to minimize the loss functions, essentially what it is. Get to the lowest point, okay? And I just want to show you one other thing here. These are a bunch of graphs and everything like that. So this is the confusion matrix. I'm not sure if this will run without having run the other stuff. Ah, shoot. I'm going to have to go all the way back. Sorry.
Is it the run all button at the top?
Yeah, where is it? It takes me all the way back.
Yeah, the double arrow will quit everything and run everything.
This one here?
Yeah.
All right, well, let's see how it goes. It's like rebooting everything.
Yeah, it might take a minute.
So I wanted to show you the confusion matrix, because it's another thing that Wes was speaking about last time, about this little box and understanding where everything falls into with your data.
Did that go?
I'm not sure. All right, well, technical difficulties. Oh, no, let's see here. The data is so small in here. Now you can also do a data augmentation. So, which is just, if you look at this image real quick, this is one image which we turned into 6 images. Remember how I said that, one pixel change can fool things? Well, this one pixel, the computer sees this as 6 different images, even though it's really on one image. I mean, even if you took an image and rotated it 1 degree, that's a completely new image. So it's fairly easy to augment your data if you do have a small data set. Sorry. So, it's going through and doing the fitting. It's giving me the same thing on the adjustable learning rates. Yep. Let's see. This is a lot of what deep learning is just sitting and watching models train. It really is. And you just got to sit there and wait and hope that you got the numbers right. You can track it a little bit in real time, but how are we doing on time? All right, I'm going to wrap up here in a couple of minutes.
This is choosing.
That's going through it. That's doing, this is an adjustable learning rate, and it's going through and changing that. It's fitting it with a cycle, and it looks at about how many it tries per cycle. So it's a dynamic learning rate, essentially, is what it is.
And it's just trying those 3 learning rates that you gave it.
Yep, so you can see the learning rate here as it changes, and it goes through. Okay, looks like we're almost there again. Woohoo! Okay, so there's a confusion matrix. It's the same as it was before. Awesome. Oh no, wait, there's one wrong. Okay, so as you can see, this is a great way to look at your results. So you see, it predicted that, it's predicted that Jack Skellington. This is the true label. It predicted one Jack Skellington as Santa. So it did pretty good. Only 1 out of 32. Or no, how many is that? Yeah, 32. Okay. So that's really it. I don't want to keep going through this stuff. I know I got to close it out. Is there any questions about the computer vision introduction to CNNs and kind of how they work? Yeah.
Any comments on the reason why there's so much more green than blue?
Oh, in the human eye?
Yeah.
I'm not sure. It has to do with luminance. It has to do with luminance. And I'm not too sure about why that is. But Bayer was the guy who kind of implemented it in computers and figured that out. So, it's an interesting thing, yeah.
Do you ever disassemble the model to try and determine how it's making the decisions that it's making, or you just treat it as a black box that you've trained and therefore it's going to make the right decisions?
Yeah, it gets really complex in there. So I personally just let it be a black box for now and build those layers. There's all kinds of papers and other things that you can find that maybe if you want to understand about how the fully connected layers work and everything like that.
After the model has been generated, you could disassemble the model to determine that, well, the reason why I picked Santa Claus images was because the prominence of red in the image versus Jack Skellington is going to have black and white most of the time. And then when you have an image that has more color than not, then that might confuse the model because it's Jack Skellington wearing a Santa Claus hat.
You're gonna have to. You wouldn't be able to go through the layers really and figure that out. You would figure that out by looking at the predictions that happen afterwards and seeing what it's predicting wrong, and then kind of looking for patterns in that. And that's kind of how you kind of have to work backwards from there to actually understand what's going on in between the layers. It's just it really is a lot of black box stuff going on. Yeah.
Fair enough.
Yeah. You could. You could definitely go through and do it. The math is there if you want to spend a lot of time on it.
I'm curious what the benefits of actually disassembling it would be.
You want to work on your math skills, your linear algebra, and that's about it. So,
Okay.
other questions? Anything else? Cool. All right. So we're going to break for a couple of minutes. We'll be back here in 5 minutes, and then we'll get started with Wes's talk on Intro to GANs. Thank you. mic'd up.
Yeah, that's fine.
I'll keep checking the streamers. Watching.
Cool.
Shut down my instance.
It's in my I forgot to share my presentation with you. So I might have to log in. If you want to, guess we could do incognito.
Yeah, just log out of that.
Or just do incognito.
Okay, very easy. So anybody here wants to talk about upcoming meetups? Anybody here running any meetups in Lancaster? No? Okay. Well, you can go, as far as I know, you can go to the Tech Lancaster website and you can check out all the upcoming meetups. I know there's about 7 to 10 that are running every month now here in the Lancaster area. So feel free to check them out. I think that's all the announcements because there's nobody else here. It's amazing. So, all right. Ready to roll?
I think I broke it somehow.
Awesome.
Not sure why it's not projecting. Aha!
So let's go here and
Beautiful.
Well, I got a question about this. You guys don't have this meetup on meetup.com, right?
we do not right now.
Okay.
Do you?
No, I just was confused because that's where I was looking for it. I had to go kind of around and find it on the
Oh, okay.
Slack chat.
You can actually visit our website, lancasterai.com, which is normally where we run it. I think the meetup site said you're going to charge something, or once it gets a certain amount of All right.
Okay. Hello, everybody. I'm Wes. Going to talk to you a little bit about something very cool today called GAN, or Generative Adversarial Network. It is brand new technology. It's cutting edge. And it's something you want to know about because it's going to affect all of your lives in the near future. And you will see very clearly why. So it's extremely popular. First paper was published in 2014 by a gentleman named Goodfellow. And since then, it has literally exploded. Hundreds of papers being published about this stuff. It's all very new, lots to be discovered. So I'm gonna get to it, but we're gonna take a little bit of a scenic route here because I want to give you some background. So before GAN, sort of the best tool that we had to be able to generate examples like pictures or audio or video or anything to create it out of thin air. The best thing we had was called autoencoders, variational autoencoder, etc. And essentially the way that works is you have a learned representation, a compressed representation. We're going to call that the latent space, and that's going to come up later. So the latent space is a compressed representation of the input or the output. And ultimately what happens is, I'm sure you're familiar with encoding and decoding is, just taking something from one alphabet and turning it into another. So in this case, we're taking, this is from the MNIST handwritten digits database, which is commonly used to test machine learning stuff. So you've got the number 2 is written, this is a picture. The picture goes into the encoder and spits out this latent representation, which is something that it learns how to do. The decoder, the matching decoder, will actually be able to take this latent representation and then unravel it back into something at least close to the original image. You can't see very well, but the second image is much blurrier. And that's been one of the big issues with the variational autoencoders, is that they don't produce a very high fidelity image. You've got a lot of loss going on, like lossy as in compression. So I want to frame this problem with the idea of mastery. Nicole knows I've been reading a lot about mastery lately. Robert Greene, Josh Waitzkin. It's really, really fascinating topic for me, and I think it really goes well with the machine learning idea of optimization. So you want a machine to basically become a master at a specific task, whether it's classification or generating a certain type of image or what have you. So, here we all are. All of you are capable of mastering something. And it's not easy necessarily, but we have some tools available to us. So I want to talk about what actually allows us to master something. Or how do we actually go about mastering? Well, from what I've read, there's some sort of special, deeper type of intelligence beyond the analytical or the emotional intelligence that we tend to value in our society, and it's like an intuitive intelligence. It's something that's a little less concrete, a little harder to describe or name or grasp, but it seems to be a common thread in mastery. And so that's what I want to try to do today. Is I'm not going to go into a whole lot of detail on the mathematics of it all, but I do want to give you a high-level appreciation for this new thing. I want to make sure that it's in your toolbox in case you are working on a problem where this could come in handy. I want you to understand how it can be applied and what problems it can solve. So let's see. So I don't claim to be a master of mastery, though I think that would be a good thing to master. I have read a bit about it, and I am thinking a lot about it recently, and I'm going to go through some tools that we have at our disposal. Probably the most obvious and common is the exploration route. So you think like a small child or unsupervised learning algorithm of any kind, really. Thinking about like fake it till you make it, project-based learning, trial and error. Just sort of figuring it out as you go. That's one way. It's not very efficient, though. We want to do better than that. So one way we've overcome the problems with exploration is we've looked into, let's try to have a mentor, somebody who already knows the path, help me find the path. You've got, a lot of situations like that. Education at a college, or you're doing trade school, or studying under a mentor, or any of that stuff. And then under these are two really great tools that I'm sure you're all aware of. There's one even better than that. Adversary. This is the real world. This is when you have an enemy. Enemy is an incredibly good tool. If you don't have any enemies, I recommend you get some. Because an enemy will keep you sharp. An enemy will make you achieve things that you didn't even think you could do. Because the enemy is always going to be trying to get one step past you and forcing you to really be sharp and on your game. So when we step back and try to apply this to machine learning, we've got some schools of thought here. Unsupervised learning is used very commonly when it's difficult to label things properly, or you don't have a lot of labeled data to work with. You can have an unsupervised algorithm. So think about like topic models, for example. I might not know all the topics say we're looking at tweets, which is something I've done with Brand Yourself. We're trying to topic model tweets. How many topics do you want? Say 10. Okay, what are the 10 possible topics of tweets? Well, it's really hard to just sort of go throughout. I've done this, I can tell you sort of what they are, but they pop out of the data naturally. They aren't prescribed. You just say, give me 10 topics out of this, and it looks at word frequency and things like that. So that's unsupervised. Supervised learning, you have labeled information. So that's kind of like thinking about a trainer telling you, no, that's wrong, that's right, that's wrong, that's right. That's going to help you learn a lot faster, but it's also going to give you a prescribed track. The GAN is kind of like the adversary tool. So that's hopefully puts that into perspective in terms of like the greater machine learning world for you. This is the one that we're going to focus on. The GAN, here it is. This is a picture of the way it actually works. So again, we have the latent space, just like with the autoencoder. We have a very compressed representation of something. In general, we're just going to start with noise. We're going to put it through some sort of filter. This could be any sort of machine learning algorithm. It could be the CNN that Rich was talking about. It could be any sort of feed-forward neural network. It could be any number of things. People are experimenting with this part of it right here a lot, and that's what a lot of the papers are about. The latent representation, just like we saw back with the encoder-decoder, the decoder side, it was able to take the latent representation and turn it into an image. So what we're going to do is we're going to set up a game. We're going to have the generator create fake images and try to fool a discriminator. The discriminator is going to tell you, yes or no, is the image that was fed in, is it a fake image or is it a real image? And we're just going to alternate, or not even alternate, we're just going to randomly, sometimes it'll be real, sometimes it'll be fake. The discriminator is going to learn very quickly, early on, to tell fake from real. And then whenever the generator proposes an image, the discriminator knows this is fake. It's going to send that information back through the network and update all of the weights, the biases and the weights. And so that's basically how it learns. I'm going to do one more. This is another picture of the exact same thing. Repetition is the mother of learning, or something like that. I thought, just in case my picture is not as good, this is somebody else's picture of the same idea. So you have the latent space. They visualize it as just multicolored squares, which you can really think of it that way. It's just some sort of noise, almost. And then they inject noise into it. If you didn't inject the noise here, the eventuality is that your generator learns to generate your exact training set, and the discriminator also gets to some sort of like optimality, like very fast, and it's not useful because it doesn't generalize. But what we don't want to overfit, as it's called. We don't want it to learn our training set. So we're going to inject this noise. It goes into the generator. We generate the fake samples. They go into the discriminator. The discriminator says, is this fake or real? And then not only that, but was it correct about its assertion of the image being fake or real? And again, the result of that comes back through the network to update the assumptions. So it's actually a game. Like Richard's description on the website, it's a zero-sum game. What that means is that every time player 1 gains, player 2 loses by the same exact amount. So it's like a scale. If one player is winning, the other player is losing by the exact same amount. The other thing is it's a minimax type game, which basically means your whole objective in the game is to minimize the maximum loss. So basically you want to reduce the worst case scenario at all times. You want to keep the worst case scenario to a minimum. And that's your, you can think the prisoner's dilemma or something like that if you're into game theory. One cool, the reason why I have Russell Crowe's up here is because he's playing Nash, John Nash, famous game theorist who discovered the Nash's equilibrium. And the solution to the game is a Nash equilibrium. So I thought that was kind of cool. So here's a visualization of what we're talking about here. The top, it's hard to see, but the top is a lot blurrier than the bottom. The top is from variational autoencoders, and the bottom is from generative adversarial networks. And you can see basically this was trained on this type of bird. I'm honestly not sure what type of bird it is. Any bird watchers? And we can see that the GAN actually does a really great job. The slides are available online, I think, too, if you want to get a closer look at these. But it's hard to tell from the slides, but the bottom is much clearer. There's a lot of fine detail that you see that you just don't get with the old method. And a lot of that comes from that enemy that's keeping that generator sharp. It's scrutinizing the details. It's saying, that's great, but it's not great enough. So I thought that was kind of cool. Oh, there was one more thing here I wanted to show you. So yes, we can do images with GAN. And here's an example, live example of what is possible. So this somebody was into anime and wanted to create an anime character generator. So this, in the browser, you just click generate, and it will generate truly unique new anime characters never before seen. Every single one is different. You'll never see the same one twice. You can even choose these conditional variables, which we were talking about the latent space. So you can say, I want an open mouth, I want dark skin, I want the blush, and then I want them to wear a hat. And then I click generate, and there, well, I guess she has a hat on. And then all the examples that come out will have those parameters set. Anyway, very, very cool stuff. Let's go ahead to this. So here's what happens when you vary the latent space. So the latent representation, when you start to just vary it systematically and just iterate through and say, what is this thing capable of producing? So this is somebody, TJ Torres, highly recommend watching his talks if you're interested in more information on this. he did this post called The Fontastic Voyage, where he tried to create fake fonts using GAN. And this is just the letter A varying over the latent space. So you can see there's different families of fonts sort of hidden within that latent space. And again, this was unsupervised, so there's no telling what's going to come out of it. It just sort of bubbles out naturally. Here's another really cool application of GAN that they did Celebrity A data set. So it's just a bunch of celebrities. These are the inputs here. And just like we were seeing with the anime characters, you can actually choose these. This is black hair, blonde hair, brown hair, gender, aged. This is hair plus gender plus aged, gender plus age, and then hair plus gender plus age. I definitely recommend getting the slides and taking a closer look at these, but you can see kind of what's going on here is like this, we're just giving blonde hair to everybody on that column. Or on this column, we're giving brown hair to everybody. Or on this column, we're making everybody look old. The gender one is really funny. You can kind of make people look like the opposite gender in their faces. I wonder if I can, nope, can't zoom in. This is another one. It's really mind-blowing when you look at this stuff up close. We have the input, and then we have different facial expressions that are able, these are generated. These are not real pictures. Everything past this line is completely invented by the machine, and it's incredibly realistic. You have disgusted, fearful, happy, neutral, sad, surprised, and it's amazing how natural and real these are. So we can do images. Can we do audio? Well, we're working on it. Here's a video.
Share with you a small announcement about a cool startup called Lancaster. They launched today their website where you can create a digital copy of your piece. They only need you to record 1 minute of audio. This is just a
So not easy to hear, unfortunately, but basically the Lyrebird, if you want to check into it, they've been able to replicate voices with only a minute of recorded audio. You know, imagine the implications of that. So yes, we can do audio. Can we do video? Here's a video from Raiders of the Lost Ark. I think it's lit. Is it? Yeah. So instead of Harrison Ford, you have Nick Cage. Nick Cage's face is put over that. So this has actually been a really big issue lately. You may have heard of deep fakes. Here's another one from Superman, where Lois Lane actually has the face of Nick Cage as well. And yeah, it's truly incredible. So one of the big issues, like I said, this is going to affect your life. One of the big issues that you may have seen in the news is these deep fake things they're basically making porno videos with anybody's face. So they're taking actresses and actors and just imposing their face on top of, you know, the adult video bodies, and it's incredibly realistic. It's scary realistic. It's almost freaky how realistic it is. So this has posed a big threat. People are worried. You know, they've already banned these videos from Pornhub, from Reddit. The whole subreddit got shut down. There's a lot of people attacking this because they're scared of what the implications are. Well, the thought leaders in the space are very aware of this problem and thinking actively about how to put in safeguards against it. One of the things is interruptible agents. So they're worried about basically what happens when this stuff is able to run amok without any sort of off button. And so one of the, there's this really long, interesting math paper about the mathematics of the off button and how to actually put that in there safely. Synthesis detection, so being able to say this is a fake image or not is a huge, huge game that's coming into play now. And those are getting better and better all the time. Fortunately, GANs, you can tell. This is a whole company based on this idea, anti-AI AI, that is able to detect whether a voice is fake or not. So if you're in public and there's an android, a human-like android, one day, or maybe you're just on the phone and somebody's calling you and telling you something, you would have this earpiece that would give you a cooling sensation on the back of your ear whenever it detected a robot. So that's pretty cool. Subtle and keeps you in the know about what's real and what's not real as we blast in this brave new world. So just to go over some other uses of this technology that I didn't already cover that are just also mind-blowing and amazing. The first one is the one I'm working mostly on, is real-time data. So when I say real-time, I mean real valued time series. So think seismograph, EKG, financial time series, things like that. So one thing I've been able to do is Bitcoin data. So like people want to train auto traders to trade on Bitcoin. Well, the problem with that is that you only have so much historical data. And once you train on that historical data, your model will overfit very quickly to that. And it also won't be ready for new and unexpected things. So a lot of people are trying to generate fake data to train the model, but the fake data is not real enough. It's too fake, and it's too algorithmic. So the GAN comes in here, creates very realistic time series data, very realistic. But it also doesn't memorize the training set, which is the key. And now that's key in multiple reasons. First of all, if you're training auto trader for Bitcoin, you don't want that. But more importantly, in medical setting. So you want to have a medical application. Well, where are you going to get your training data? Well, medical data is locked down pretty hard. It's not easy to come by. A lot of times you have to have a special status, or you have to apply, or even when you do train your model, what's to say that that personal private information is not somehow embedded in your model and could be tickled out? Well, a lot of research has gone into that, and GANs work really well for that too. They successfully protect your personal information. None of that stuff comes through. You've also got 3D models. Imagine being able to take a picture of something and then turn it into a 3D model. That's pretty freaking cool. They can do that with GAN. Super resolution, taking an image that is low resolution and making it high resolution. Just the idea of that, pretty mind-blowing. Text to image. This is something that you've seen a lot of the AI applications where we have a picture of something and then the AI is able to describe what's in the picture. What if you could go the other way? Well, you can now. GAN does that. GAN can take a description, a purple flower with a yellow center, and it will create a picture of a flower that looks real. It looks very real. And it's a flower that no one's ever seen, that never existed before. It's pretty amazing. Face-to-face, that's something we saw earlier with the Obama video. They're able to take somebody's face and impose the expressions onto another face. So, for example, in the Obama video, they had his mouth and his lips moving to the words, even though Obama wasn't actually saying that. You've got image search. So one of the things that people are using this for now is you might have a family symbol or a coat of arms or something like that that may be written in documents. And it's really hard to find just a handwritten symbol, an old, just on Ancestry.com or something. So what you can do with a GAN is it sort of learns the general idea of what the symbol looks like, and it can search very efficiently through that stuff. Another one, disentangling foreground and background. Imagine being able to just remove the foreground out of an image and you just left with the background. GANs can do that very well. And learning style transfer. This was another really cool one. So you can take a picture of something and then make it look like Monet painted it. Or you can take a picture of something and here's some pictures of that actually. Really cool stuff. Let me go ahead to this one and then we'll go back. So here's Monet. And again, please take a look at these up close because they're really going to blow your mind. Monet, this is a painting that Monet did. And then they were able to translate it into a photorealistic photo. So it actually looks like a real lake and stuff. It's really amazing. Then you could go back the other way. You can take a photo and make it look as though Monet painted it. Similarly, we have zebras to horses and vice versa. We have summer to winter and vice versa. And then down here is another example of one photo in several different artistic styles. If we go back, a few more cool examples here. The input is an outline of a bag, and it actually fills in a very photorealistic leather bag. And the other really cool thing is, if you just keep hitting go on the GAN, like you plug this in and you just keep hitting go, you'll get a different bag out every time, kind of like what we had with the anime. It injects some noise in there, and it's random, and it just sort of generates a bag. Obviously, it's dependent on the training set somewhat. We've got here day to night. So we took a day photo, turned it into night. Here we just drew some squares, and it turns it into a facade. And then same thing here. We have some basic shapes, and then it fills in all the details of a car scene. Let's see if I forgot anything. So I think that's it, actually. Yeah. So any questions about GANs or anything I talked about?
How big are the training sets, and how long does it take to train, those kind of questions?
Yeah, it's amazing actually because these GANs, they learn very, very fast with very little data. So you saw with Lyrebird, the audio one, they're able to create a fairly realistic replica of your voice that can say anything. They can make you say anything with only 1 minute of recording. And again, the power of an adversary is really showing there. Yeah?
So is the main point of this technique or approach, is it the generation, the discernment, or both?
Both. You get 2 for 1.
Okay.
Yeah, I should have gone in. That's a really good question. You get 2 for 1. You generate a discriminator, which is basically a classifier, binary classifier. And it works well to say real or fake. It doesn't work well to say, Parker Bird, but it does work well to say real or fake on this one thing. So it is very targeted classifier, if that makes sense. And the generator has a lot more obvious uses. So I think that's why you see that sort of skew towards generating. Yep. The other cool thing I can add to that too is with the real valued medical time series, they were able to train other classifiers from fake data that performed very well on actual real data. So if that makes sense, the generated data is so real that you can train classifiers from it, which is one of its big uses is people are, data is scarce, especially labeled data. Well, with GAN, you can create labeled data out of nowhere, and pretty freaking cool. Any other questions? Is anybody worried about their voice being used? Or
I think I need to do a lot more research before I can ask a knowledgeable question.
What do you think are some of the ethical challenges that are going to happen in the next couple of
Yeah, I mean, ultimately, you know, imagine if I had in my computer at home, I could create a fake Rich on video chat with someone, and it would sound like you, it would look like you, I could make you say anything. You know, I could agree to contracts, I could transfer power of attorney or something like that, you know, unless there was something that prevented me, like having to be in person or whatever. And, you know, there's all this stuff I've read about on Facebook, for example, people using video chat to lure people in and then blackmail them and things like that. There's all sorts of stuff that's scary with that front. You've got, I mean, obviously the porn thing, we talked about that, like lots of people are scared about that because it's very easy now. You can actually, the deep fake thing, you can download an app and you can, any of you could do this with no prior knowledge. Just go download the app, upload a couple videos, click a couple buttons, wait 6 hours, and you have a fake video of somebody else. So, I mean, major potential there, I think, to do wrong, which is why a lot of that's happening. What you got?
Well, it seems like there's another side to that too, which is that something is real. You say, well, that's fake, right? That somebody just faked that, but it was really the truth, right?
Very, very interesting point. So definitely goes both ways. Definitely goes both ways. I didn't even think of that. The good news is that GAN is pretty easy to detect. We can detect that something's generated with GAN. So that's a big hurdle that will have to be gotten over in order to you know, cheat those detectors.
Isn't cheating the detectors just another adversary for
Yeah, exactly. Yeah, so we've got sort of like the butter battle book or whatever going on here. But this could be, I mean, you know, Russia is doing all of their warfare online now. And they've stated that very clearly. So that's where the battlefront is online now. And these are the tools of battle. So this is the stuff that's going to be coming out. We're going to have to be watching out for with, you know, especially politics, but any sort of social media and whatnot.
I mean, just the deepfakes issue alone. I mean, does a celebrity have the intellectual property rights to their own appearance? Does anybody have the intellectual property rights to their own appearance and voice and disposition and everything? And that's something for legal teams to tackle. I don't think that's effectively answered right now. So interesting.
And how do you even define your likeness, you know?
Right? Yeah.
Yeah, there's really no legal framework available
Interesting philosophical.
that I know of.
About that, yeah.
Interesting for a lot of dead actors and actresses too.
Indeed.
They had that one of the chocolate commercial that used
Their estate and
Audrey Hepburn. It's a great commercial.
or can you license your intellectual property rights and appearance to some other actor?
Yeah, maybe there'll be a lawyer fee to copyright your appearance.
It's a whole different branch of, you know, being a lawyer.
Yeah.
It's sort of a current branch, you know, if you could try to using more traditional techniques, Audrey Hepburn acting, you know, without licensing it from her estate, you know, you'll get sued and you could probably lose. Although I get that they're on some, you know, in that case it seems like you'd probably lose. In other cases it might be a bit rare. You know, like, but you know, so you know, there clearly is a legal framework for reusing people's likeness already, regardless of how you go about that.
Yeah.
I mean,
Yeah, I think you're right.
The legal system isn't there yet. It's, you know, how do we detect and what might change now that it's more easier, you know, a cheap program instead of skilled artists.
Yeah, or if you have anonymity, I mean, how do you go after them, you know, and stuff like that.
Right.
So,
Will the identification of the GAN be sufficient enough to say, well, it's clearly a slightly different non-infringing right.
What's stopping things from detecting GAN detectors?
Right. Yeah, I think that's what we were talking about, like
Yeah,
the Butter Battle book. Yeah, the adversary
Cold War kind of
Yeah.
deal.
again.
It's just kind of like, they don't know that we know that they know that we don't know.
Yeah, your AI detector earbud thing made me laugh because I'm just like, that'll be fine for a finite period of time.
Right. Obsoleted very quickly, I'm sure. So stuff to think about. Obviously, I'm not a super expert on all this. I don't think anybody really knows the full breadth of where this is going because there's a lot to be discovered. But if you do read something interesting or think something interesting, I'm very interested in it. So definitely would love to talk about it more with you guys.
Oh, we look to science fiction for that. Right, with the people leading the way on seeing the ramifications of the technology we're developing today.
Absolutely. Is that all?
That's it. Thank you, Wes.
Yeah, thank you guys.
All right, everybody, that's a wrap. Thank you. We'll be scheduled out on the last Tuesday of every month.